I'll introduce you. Hi everyone, welcome to today's Bangalore Theory Seminar. Today we have with us Ayush Sawarni. He is a first year PhD student at Stanford, working with Vasilis Kyrianis. He was a master's student here before that, and he also spent a year at MSR. And he used to be our local bandit expert when he was here in Bangalore. And now he is doing some amazing research. So let's welcome him. So all over to you, Ayush.
Uh, Thank you so much, Nijar. It's great to be back here. So, today I'll be talking about. Okay, actually, I have a mic here. So, today I'll be talking about preference learning with response style. This is joint work with collaborator Sarsujit and my advisor Vasilis. So, learning for human preferences has become quite ubiquitous in machine learning. I'm sure a lot of you would have seen this. Um, just to illustrate, it's it's actively used to train robots to walk in a certain manner, to for diffusion models to align images to a certain like human aesthetic, or you might have seen ChatGPT generate two options for your query, and essentially it's trying to figure out like learn from your preferences. In all these situations, the reason why we need learning from human preferences is because a lot of times the aesthetic factor that a human prefers is not cannot really be captured using a loss function. So you may minimize some loss function to get a robot to go from place A to place B, but getting it to walk on two legs in a particular manner is a more of an aesthetic choice. So the way this learning from preferences work is that you collect some data from of human preferences, and on top of that, you learn a reward or a utility function that captures how much you value a certain choice. And with this reward function, you fine tune your model. That's the classical approach. These days, people have like an algorithms like direct preference optimization. What people are doing is that you can instead of you can just bypass this reward learning phase and you can directly learn fine tune your model as well. But implicitly, you are learning a reward function because you assume a reward structure and then you get like a closed form expression of the policy of the loss in terms of directly your policy. So if explicit or implicit, you are ultimately learning a reward function. So formally, the setup that we'll be looking at is that you are given two choices, x1 and x2. And based on that, you make a decision, y. That's a binary decision, which is either plus or minus 1. X1 and x2 can be vectors. It can be actually any objects, doesn't matter. We assume that this decision is governed stochastically based on some underlying reward function that is unknown to us. And the objective is that given n such samples of x1, x2, and y, you want to learn a reward function. This is a standard preference learning setup. The way you learn this is that you assume some structure, you assume some relation between these tuples and the reward function. And one such assumption that is very popular is known as the Bradley-Terry model. That is, we assume that the probability of choosing option x1 uh, given x1 and x2 is just the sigmoid of the difference in rewards. So given this model, how would you go about learning the reward function?
Like there's no e to the minus beta x or something.
Yeah, so that parameterization, like typically it just becomes like a hyperparameter. So I just assume that.
That line of work in the econ econometrics, like a revealed preference, which again, but I guess what sort of distinguishes it is like the that you're forcing like this Bradley-Terry model and not sort of another function class. So it's that again, that's kind of a yeah.
Yeah, like I feel like there's a whole literature on how do you make this model choice, and
Yeah.
how do you fit like sensitivity to Bradley-Terry, or like can you sensitivity analysis? Yeah, but like we just assume that.
Okay. Yes, I mean, this standard practice here, but with reading preference does this exercise a bit more systematic,
Okay.
which is among the like, many models by and which.
Yeah. So when you do maximum likelihood estimation, this like essentially boils down to minimizing a log loss. This is a logistic regression problem now, and this is what the loss will look like. I'll just simplify the notation a bit. Just to denote the two choices, I'll just denote it with X. And I'll use Rx to denote the difference in rewards between the two choices. So this is what as a function of reward difference, this is what the sigmoid looks like. If you notice in these regions, the derivative of this function with respect to the reward difference is very low. And what this essentially means is that in these regions, if you're getting signals from these regions, it's actually very hard to differentiate or figure out what the exact reward difference is. We'll see this formally soon. And with response time, that's one of the issues that you're able to address. Uh, So what is response time? Basically, is just that you, while collecting the data of binary choices, you also recorded how long it took for the user to make this decision. And intuitively, what we're trying to capture is that a shorter response time would entail that you have a stronger preference. This is not something that we're claiming. Like it's a well-studied thing in cognitive psychology, neuroscience, and in fact even in economics. So there's like 50 plus years of research on modeling preferences using different models. And what mostly like most of the researchers concluded to is that you model it via this drift diffusion process. And various parameters, but broadly it's like a diffusion process that you use. And in fact, like the Bradley-Terry model can be derived from such a diffusion process model as well. What we consider is this EZ diffusion model. I'll explain what this exact model is, which was by Wagenmakers in 2007. And how the decision-making process under this model is that uh, based on your reward difference, Rx, recall Rx is the difference of R of x1 minus R of x2. And the decision-making process happens in the following manner. So as soon as you see two choices, you spend some non-decision time encoding those choices. What this encoding means can just is an abstract term. It's just some constant or varying time, which is not random. Now, once this is done, you decide why after some evidence accumulation phase that lasts for capital T duration. How this evidence accumulation works, I'll explain soon. Uh, this evidence accumulation is what is modeled as a diffusion process. So this diffusion process is essentially a drift diffusion process where you have a constant drift. This constant drift the constant in the drift is R of x, and you have two absorbing boundaries. So basically, T of ET is the evidence accumulated up until time t, and this follows from this. You have this constant drift at every time, plus some white noise Gaussian. And a decision is made as soon as you hit one of the boundaries at plus or minus a. So as the response time or the time taken to decide is just the time at which this evidence becomes either plus a or minus a. And it's one if you hit the top boundary, and it's minus one if you hit the bottom boundary.
Like a one-dimensional random.
It's a one-dimensional random. Continuous. And with this model, now the new objective is that now you have x1, x2, y, and response time. And now again, you want to learn the reward function. So note that only with this you could learn, but what can we do something better with this extra variable if you have it? This is just an illustration how this would work. So again, like this is this non-decision time, and for different number of, so like if you have a strong preference, you typically see because of a strong drift, you'll quickly converge to the boundary. With a weakish diffusion process, you might, like, even if you have a positive drift, you might end up going to the lower boundary, which again, like holds with whatever intuition we have about this. Now, what properties do we have? So you can simplify that stochastic differential equation that I wrote, and you can get some bounds on the moments of this process.
It has to be some parameterization.
Exactly. That's what I'm coming to. So that's that complicated looking diffusion process does simplify in some nice ways that you're able to exploit. Oh. Yeah.
To distinguish strong preference, weak preference.
Yeah.
We use, instead of response time, we have some score, right? So when collecting data from the users, we also ask them to give a score.
Yeah.
So does the response time
That's well
better than
So the reason why people did study score based, ranking based models, a lot of these models, what was observed was that like binary preferences requires very less cognitive load on people, and so like binary preferences work well. The good thing about this model is that you're not asking them to do anything more. It's just some free data you collected additionally on top of the binary data. I guess like people are already recording that. So that's the reason to use this, at least.
available?
We could not find. There's some data set on preferences, some like food menu preferences, but it's very few samples. So like certainly not useful for this. But we have some synthetic experiments that I'll talk about. But like in psychology literature, people have verified that these models do model this human preferences. And in fact, like so, the first point that I wanted to say is that if you calculate probability of y equal to 1 given x in this model, it becomes exactly the Bradley-Terry model. Additionally, you get some expressions for expected time given x, which again, like the expected time can also be calculated in terms of the reward differences if you knew it already. Using combining these two, you get a very nice expression for the reward function. If you knew these ratios, you're done. But this is still not in a very learnable, like we just want to learn the reward function. So it's not like a very learnable form. We actually want a loss function out of this.
Error in the denominator.
That's precisely the problem. Okay, so going further, we assume that A, the boundary, is known, and the non-distant time is also known. This is in fact becomes a modeling choice because the non-distant time, the time taken to encode the information will depend on what application it is. Like in language models, you might depend on the text size. We can assume to be known without loss of generality. It's a scaling factor. In fact, like if you don't know A, you can learn the reward function scaled by A. So how do we learn R? First thing that you should try is MLE. Unfortunately, the likelihood of this diffusion process is not very tractable. In fact, like if you the density of this response time T looks very ugly, an infinite sum. So maybe you could work with this, but I don't know how to. So the obvious thing that I showed before is this. We try to use this. And in fact, like notice if you knew the denominator somehow, this becomes like a scaled regression problem. You just want to regress R on Y, and Y scaled by this quantity. And that's exactly the first loss that we'll consider. That we just start with this naive loss function. So y minus rx times expected t given x whole square. Note that we don't know this. So what the obvious thing to do is that treat this as a function of x and now learn this function as well. The problem is that the loss function is now very sensitive to t naught, and learning t naught can actually be hard. I'll okay.
You're only getting like the final convergence time and not the actual trajectory. If there's a random walk happening and you know when the random walk is terminating, and no idea of how it converges.
But P is that final time. We just need a sample being
So it's conditioned on.
You condition x, so you're learning a function. You can do regression with a function t and capital T, and you can learn t. But it's when I say it's hard is because of certain, let's say like one example is that the function itself can be very non-linear. So even if you have a linear reward function, the time function can be highly non-linear. And like if you plug in theta x and then try to minimize, do regression with Rx plugged with theta times x, it will in fact be non-convex in theta. So it's unreasonable to expect that you'll learn like t that well, right? And the second thing is um, you actually don't really observe just t, but you're observing this whole thing. So if your model is slightly misspecified, that can also cause issues. And third, I feel like this is the major problem is that t can have heavy tails. As like in fact, as the reward difference goes to 0, your MGF goes to infinity. So t is what people in statistics like call it a nuisance function because you don't really care about estimating t accurately, like as long as you get r, right? So this is essentially a nuisance, and the objective now will be that can we make this loss less sensitive to the nuisance parameter, and that's what people have been uh, studying in semi-parametric statistics heavily. Uh, One such technique is this orthogonalization, which I'll now cover. So Neyman-orthogonality concretizes this notion that you want loss functions to be less sensitive to the nuisance estimate error. And to define Neyman-orthogonality, I just need to define one quick thing: is that how do you take derivative with respect to functions? So you just take directional derivative. So let's say f is a functional from a function class to a real number. So think of f as a loss function that takes in your deep neural network or whatever, and then maps it to a real number. And the derivative of this functional in direction h at f is defined as you just move f in the direction of h by some scale and multiply it with some scalar t, and then just to simply take a derivative with respect to t and take like limiting t equal to 0. The standard directional derivative definition. For a bivariate functional, just imagine these are like partial derivatives with respect to theta and g. Now the loss is said to be Neyman orthogonal uh, at theta naught and g naught, where theta is the parameter of interest and g is the nuisance. If first you take the derivative of the loss function with respect to theta, and then you take the derivative of that derivative with respect to g. That goes to 0 for all direction h and k. What I'm essentially saying is that the gradient of the loss function with respect to theta is less sensitive to your nuisance parameters. That's huh? It's in all directions, sure. Yeah. Like if you have vectors, then it will be a matrix.
change the order of the derivative. Why is the order link? Is the order same?
So I believe for like simple function classes, like parametric classes, you can change the order. Like closed and bounded. Yeah. Yeah. Like if that's 0, then that implies this is also 0. But I'm not sure about like general function classes.
Point is G, like you first take the derivative with respect to G because like exactly the reason that you encounter T. Like you have to first estimate this new your ultimate goal is still theta.
Yeah.
So what this is saying is that yeah, like small perturbations in
Find the local optimum.
yeah, and then
Around it.
yeah, it doesn't matter.
So if your gradients are less sensitive to G,
Yeah,
that suffices.
but all errors in G.
Yeah. Oh. So there's a lag.
Sense.
So this is the orthogonal loss. Okay. So I just want to remind you that we had y minus rx dx in the previous naive loss. We just add this extra term, and this becomes Neyman orthogonal. What is?
Care about whether it's
It will be biased because of this nuisance error. Your theta will always be biased. Just you want to reduce that biasness. So t, in fact, oh yeah, by the way, like if you substitute t naught here, this will remain unbiased. At least like if you take gradient, it will still remain unbiased. Because this t minus t naught cancels out. Um, T was the nuisance that we saw earlier. We have this additional nuisance parameter that is again an estimate of the reward function itself. Might seem counterintuitive, but what we demand from these nuisances is that these T is a crude estimate of T naught, and R again is a crude estimate of the two reward model. We don't really have very high expectations from this. This R can again be calculated simply by using log loss, right? Like you just optimize log loss and you get an R function, which might be not that great an estimate. So then once you have this, you just optimize this loss function where this cal R and T are like not hyperparameters. Like this loss function is parameterized by this, but you're actually optimizing only on R. In practice, this would how you proceed is as I just mentioned. Like you take the data, you learn T, you learn R using log loss, and then you further fine tune it. The same you can either do the same data, or you can do some data splitting on, and then learn this R on top of that. Uh, yeah, I'll give. It can be like if you typically need root and convergence, n to the power 1/4 convergence suffices to get root and rate.
maybe we could circle back to that later, but like somehow it's like by just two stage. I could have like done it very iteratively. Yeah, I could have given R1 T1 and then
That's so
T2
yeah.
and then
I've been wondering about that actually. In fact, like generally orthogonal statistics, that's a question that I've been curious about. That do it in an online fashion, like
yeah.
estimate one and then that will help you estimate the
Yeah.
second. But yeah, this project we even like doing this in online fashion is not clear
Yeah.
how you do
This is like this phase, like in bandits, you have this like explore phase, you hard stop
Yeah.
and then explore phase.
Yeah.
It's a fairly long jump, but better results are like it's more smooth.
Yeah. Like UCB, you don't really have this hardened.
Yeah.
Yeah.
But here also you do this, right? With the data splitting, one split you would learn T and R,
Yeah.
and then another split you learn smaller.
Yeah. So I think it will be very useful when you don't really know the total number of samples you're going to get. Like if you know, if you get all of the data, not sure if that like splitting it into phases will help. But if you don't know the total amount of data you're going to get, then how do you divide the data between nuisance estimation and that?
But in supervised setup, you can do this data splitting. Right?
Yeah. In fact, you can also not do data splitting. But then the requirements like the complexity of like the sample complexity of estimating R also involves the properties of the G function. So data splitting, in fact, like if you do data splitting, huh? It gives you a clean bound. So let me skip this proof. Okay, I think we'll run out of time. This proof is just using that definition and proving that the derivatives are zero for this expression. And the main idea is that this expected t given x is t naught, and since we are calculating the directional derivative at r naught and t naught and cal r naught, so everything cancels out.
What is the property of Neyman-orthogonality that you have used?
So I have a very short cute proof for very like simple scalar just to show how it gives you good error rates. I'll come to that.
But it's there that you will invoke this property. That
Exactly.
given that your the estimator was Neyman-orthogonal, you have good error rates.
Yeah. So recall. So I'll just quickly instantiate like some results for linear reward functions. So recall like the non-orthogonal loss is this, and the orthogonal loss looks like this. We can show that if you minimize this, you can get asymptotic normality. So which means that theta hat minus theta naught root n times this converges in distribution to a normal multivariate Gaussian with some this covariance. And what we need from the nuisances is just this. So we just need some sort of slow rates. In fact, like the requirements are more general than this, but this suffices. Like t minus t naught converging at the rate 1 to 1 minus 4, and this converging at this rate suffices. This is like the L2 norm, and D is the distribution of your like data points. So expectation t minus t naught x whole square. Yeah. Yeah, because we do expect it to converge to zero over time. I mean, no. You don't need it to be unbiased. Yeah, we just need like some asymptotic convergence. No. As long as you asymptotically converge to the true parameter. Yeah. You need consistency, but not unbiasedness.
You never need it per se, in the sense that as long as it's converging wherever it's converging. I mean, hypothetically, you could just subtract it out and get the expected value, make it like shift it back. So it's always any such statistic, you only need convergence. But yeah.
Yeah. Like there are a lot of cases where you do not have unbiased estimators, but you still get good convergence rates.
So in fact, every self-respecting one is
Yeah. Biased. Yeah. Like MLE oftentimes is biased. So if you were to get some asymptotic normality for this, you would need this kind of rate. And the rate again, like I was just repeating what I said before, but like this can be bad to us even for linear class. It's bad because yeah, it's non-convex in theta, and like heavy tails and all. In fact, like if you do, oftentimes this is done for like in high dimension sparse regression settings, and there like what we did use for experiments is that you just estimate t using some kernel ridge regression or neural networks. So for kernel ridge regression, like this non-parametric rates do apply, and you do get these kind of rates, but you oftentimes don't get root n rates for these non-parametric regression points. Now coming back to just using the preference data, you do get asymptotic normality with the following covariance matrix. Now if you look at this, like the covariance matrix dominates this matrix, where your the covariance increases exponentially with the reward magnitude, as you may have noticed in like if you've studied logistic bandits. So what we show like what you can see in our result is that the our loss is in fact like bounded polynomially with respect to the reward magnitude. There's like a big jump. We do observe this in experiments as well. Now coming back to the question that you asked, so why does like Neyman orthogonality help? So let me just set up a very simple problem. So assume that you have some strongly convex loss function, and it's like 2 alpha strongly convex. And let's say the nuisance and the parameters are just linear quantities. Oh, sorry, real quantities, scalar. And let's assume that theta naught is a true minimizer and first order criteria is satisfied at G naught.
So response time, you're able to bypass that exponential
Yeah.
dependency in that first derivative of
Yeah, exactly.
that is completely bypassed.
Okay.
Else you can separate.
So suppose again this Neyman orthogonality, this like for scalars, this is what it will look like, right? This is 0. And also suppose that the double derivative of the derivative with to theta is some bounded quantity. And suppose that theta hat is what you estimated if you had a g hat as an estimate of a nuisance. Note that this is not a like you in practice you'll actually be optimizing an empirical version of this, but let's just assume that we actually get to minimize the exact population loss at g hat. With this, I'll first invoke the strong convexity. So this is like strong convexity. If you do Taylor expansion, you know that this quantity will be lower bounded by this quantity. Next, because theta hat is a minimizer, you have that this is positive. And now we use the first order criteria. So since if I were to take derivative at theta naught and then multiply with theta hat minus theta naught, this thing by first order optimality would be greater than 0. Right? So now this gives me a nice expression. So what we have is theta hat minus theta naught times the difference in derivatives. Now again, I do this Taylor expansion, and now I take Taylor expansion of this quantity. So you have theta minus theta naught, and this is like the first order Taylor expansion at G naught, and then this remainder term, the second order term. Now notice this is what we had, right? This is by Neyman orthogonality, this quantity exactly is 0. And here you go. So this cancels out. So what we have now is that the left-hand side is upper bounded by this difference and this extra term. Now what we do is simply AMGM. So you multiply this root alpha and divide this by root alpha, and then you just do AMGM inequality. And you have this difference term which will cancel out. And then you have g hat minus g naught to the power 4 term, actually. And simplifying this, you get this. So theta hat minus theta naught whole square becomes some constant times fourth order dependence on this error. Exactly. Uh, Now, like a natural question to ask is how do you get these orthogonal losses? I won't get into that, but for like under very mild assumptions, you can actually like take any loss with some nuisance, and you can orthogonalize it and get like what they call D bias losses. And like I'll recommend you to get this paper. That's where we started as well. Now coming to results for general function classes, I won't really go into too much detail, but what we have is slightly notation heavy, so let me go through it slowly. So suppose you have some rate of convergence, because we are giving it for like any general class, we assume that R belongs to some class such that for any G hat, you have some convergence rate. So this could be root n, this could be n to the 1 by 4, whatever. What we really desire is that if you like whatever rate you had here, that is ultimately the dominant rate at which you converge to the true R hat. And like the error in G hat comes in a second order term. And that is exactly what you get. So if you have such a rate, then you can show that R hat minus R naught, uh, this rate actually goes down, is dominated by this rate, and then the dependence on nuisance rate is 4 by 1 plus alpha. Alpha is some constant between 0 and 1. For many function classes, you can just treat it to be 0. Um, so, oh, by the way, G is the nuisance function tuple that we saw before. And this is like a custom norm that we define on the reward function class. The reason is that we are able to instantiate it with for various classes. So for example, for RKHS with polynomial eigendecay, you can show that the rate of convergence is exactly dominated by this term, which means that you get oracle rates. Had you known T naught, whatever rate you would get, you get the exact same rate with this loss as well. You can also do it for VC classes, but VC classes, there's some issue, like you need some well-behaved condition on fourth moment. So like you expect that this L4D and L2D are like close, like are multiplicatively close to up to some constant C. If that's the case, then you can you get again oracle rates. Okay, coming to some experiments. So we did do it with linear rewards. We learned the nuisance functions with some neural networks, and we see that like this exponential scaling with log loss, and we see that like with ortho, in fact, with both in this case, you get pretty good mean square errors. And further, we did this for an image data set, so text to image data set. Okay. So in this text to image data set, as you actually asked, like there are no data sets where you get response time. So there's a semi-synthetic experiment in the sense that T was generated by our model, assuming that our model is correct. But with that, we do see that assuming that so there's this data set called pick, which is crowdsourced data on text to image and human preferences on that. And then based on that data set, they have calculated the score called pick score. And that pick score is actually used as benchmark and vision data sets right now, like a lot of times. And we use the pick score as a true reward model. And with that, we simulate the response time. This drift diffusion process. And we do see that like
You also have class A and minus A.
yeah, we assume plus minus 1 as in. We do it for all cases as well. So you see like good convergence. Additionally, like we see that while so this is like if you use this, if you were to use this reward model to actually finally employ it as a policy, you do see that the regret converges also is significantly better than the log loss and orthogonal loss.
So different in terms of how close is the learned R to the.
So the closeness of the R is this, and if you were penalized the reward difference every time you made the wrong decision, that's regret. Finally, I just quickly wanted to talk about this implicit reward learning. So something like, can you do some DPO style objective where you don't really learn the reward function? And um, you can do something. So again, you do like a two-stage learning. You first learn policy only on the preference data. So let me call that policy phi1. Now, what all these DPO literature, if you're familiar, what they do is that you can actually plug in reward as a function of the policy. So phi x1, phi x2, these are like policy values, and you can just plug in the reward function as a function of policy, and then you simply minimize your loss, whatever your favorite loss function. So what DPO people did was that you just plugged in this R, and then you just minimize the log loss that we saw initially. So you do the same thing. You to estimate the screwed loss, you do plug in phi1, minimize the log loss, you get some policy phi1 that is sort of a crude policy. And in the second stage, now you just plug in this as a nuisance. So a slightly modified version of the loss that we saw before. But again, this loss function only has cal r as a nuisance parameter, and p is actually just plugged in as directly in terms of cal r. And turns out this is also Neyman-orthogonal with respect to r. Now, once you have this loss, you do the same idea again, same trick. Plug in r in terms of the policy that you want to learn. And now you can now simply minimize this whole thing in terms of pi. That's all. That's the talk that I want to give. Are there any questions?
So you get the similar results for DPO study.
So DPO doesn't really have theoretical results, and we didn't really do experiments. So this is just a pitch for people to try this out on large scale models.
Now there are a lot of theoretical results
In DPO for LLM training.
obviously, assuming a class of policy,
Okay.
say linear mathematics policy,
Okay.
right? There are results. So you can this is the possibility.
Okay.
So better there result. In that result, you can find
Uh-huh.
in the estimation error so that
So you're saying like I'll get some guarantees on some like L2 or some difference between pi and the optimal pi naught. Okay.
obviously the current guarantee you can see that first derivative of your link function, sigmoid function is there. So that
Okay.
issue is there in the current guarantee.
Okay.
So your method can now be used
To
to overcome.
okay. Okay, yeah, that's an interesting direction. Yeah.
It's like other forms of like this certainly does work.
Yeah.
If this particular expression, I'm wondering like, is it understood that what like can I? So the idea is like you get one like script Rx, which is a crude estimate. You now define like an orthogonal statistic and get a much
Yeah.
better thing. But there could have been other forms, right? Like
Yes, you can. You actually we have like a family of
okay.
orthogonal losses where the nuisance you can modify. So like you can also have expected y given x as a nuisance and then t as a nuisance, and then you get similar rates for that as well. In fact, like you would use that kind of nuisance when you don't know the decision boundary a, the a and plus minus a that I use, and like we show like even experimentally and theoretically you get the same rates. Yeah. Um,
Okay.
yeah. Is there anything that you want to see? Like I can maybe discuss.
Get the proof somewhere at some point.
Okay, sure.
It's too much, then you can see.
It's not too much. I think it's. I was initially not planning on adding it, but then I added it in the end because it essentially follows from just the definition. That how do you prove this double derivative?
Let me ask like a related. So is this somewhere applicable in bandit stuff? Like
Yeah, that's why I asked. Like that's the question that I'm curious about, but because All these use like standard concentration inequalities. Some martingale style dueling bandits is exactly this linear setting that I talked about. Yeah. Firstly, that, and also, how do you do this nuisance estimation online? That phase thing could be one idea.
It's sort of explore it. Like it's just literally like
Yeah.
you just some small. You just fact that it's good n to the 1/4 versus n to the 1/2. And so you spend some time get a bad estimate and then good. But even you can probably do like a doubling thing, like some a better improved it. You not just go from script R to R, but like script R1 and a better script R2 and a better script R3 and so just kind of yeah.
Yeah. So like for example, in the logistic bandit problem, you have parameterized assumption on T on R, but like we then need to crucially like figure out how are we learning T? Are we directly optimizing T, and what rates can we get? So we here like just use it as a black box. Assume this rate exists. There you actually have to calculate this. Yeah, you'll typically read square root of n, right? Yeah. Exactly. Yeah. But
No, you can spend like square root t time. Then you get one. T to the minus 8, right? Spend square root t times. Then you t to capital T to minus 8, right? Hello.
since you need n to the power 1/4, you can spend like root t rounds for learning.
That translates into 1/2.
Nuisance parameter rate, if you spend n samples to learn the nuisance parameter, n to the minus 1/4.
Yeah. So what you need is root n rate for the nuisance. Uh, you need n to the power 1/4 rate for the nuisance, right? So if you get like that means that you can use root t samples to get the same epsilon error in nuisance. Yeah, because like so if you're using n samples, you're getting root n rate, right? To get root n rate, you just need n to the power 1/4 samples for nuisances. So that becomes like yeah, root t samples bounded. But
I mean, the other aspect is also more interesting, right? It's not just the fact that you've saved on sample, like saved as a function of it. It's the fact that the range dependence on the range parameter drastically. The exponential to
yeah,
that's also a big.
yeah. Also, another thing with that would be so for like if you're doing like a batch thing for logistic bandits, you typically have this optimal design kind of idea, right? Which is optimal for learning reward. But is it optimal for learning T as well? That's not clear. Very accurate in T.
We should probably the question is there more like a better, let's say,
Mhm.
better than like optimal design, like a better design idea
Yeah.
that has a worse learning rate, but is say much better computationally. Yeah.
Yeah. In fact, okay, I should have mentioned this earlier. So there was a paper last year in Europe that again works with easier diffusion model, and they do this. They call it a bandit setting, but it's not exactly a bandit setting because you're just minimizing simple regret. So you just take T samples and you're just estimating theta. Same thing, but they have this additional flexibility of you choose what data you want. So that's why they're calling it active. And for that, what they do is they just directly, because for linear functions, you can have this optimal design idea, right? So, and when you do optimal design, the support of arms that you pull is very small. It's in fact like D square, I think. Yeah. So for just D square support, you estimate expected t given x pointwise for each of those d points. But that does not translate here because here you're getting things from a distribution. So that approach will not work here. Yeah, but then again, they do simple regress. They don't have Martinez style inequality.
Are there ways to? I'm wondering, like, if I give you some other statistic, would just even sort of. So
Yeah. In this model, there's another like we don't have an have a with what is the optimal thing you can do in this model is not very clear because we just used one moment inequality equality one moment expression here. But let's say there are like you can derive expressions for other moments as well in terms of these parameters, and maybe you can exploit that. Like you calculate variance and then use that to estimate response. Those things are also that would be interesting as well.
Hi, Ayush. Can you hear me?
Hey Rahul. Hi.
Hey. So quick question. So I was wondering if there's an easy extension to the following setting, which seems interesting in the LLM literature. So let's say that you're now considering one distribution from which the examples are derived. But let's say there's like different parts of it, like coding, creative writing, and so on. So there is like a bunch of them, and you want some sort of group robustness.
Mhm.
Or rather, you want not just the MLE over the entire data set, but you want good good accuracies over all of them, or to minimize nuisance over all of them.
Yeah.
So, is there any extension to that setting, or is that interesting at all?
I think yeah, this can be extended like the so what we did as so like what we did assume here is that you have homogeneous users and homogeneous queries. Right? Like the model remains constant throughout. And in pure preference learning literature, they have looked at these heterogeneous preferences, where I think the heterogeneity can be task dependent or user dependent or user group dependent. Uh, does that like does that relate to what you're asking?
Right, right, right. That's related, but you're talking about different reward models. I'm more concerned with different data sets from which these preferences are derived. One is say coding, one is say creative writing or whatever. So you want bounds on all of them together simultaneously.
I see. But you
Is it
expect the
an
model.
easy extension, or is it does it seem not so straightforward?
So it's certainly not easy. And if you consider the following case that for each of these problems, the underlying model might change, like the decision making model might change. So the time taken to decide, like the time taken to encode that problem might be different for different tasks. Right? Like if it's math versus say essay writing, the time taken to encode that like t might change, the T non-decision time. Also, they like in psychology, the people use the decision boundaries to capture how conservative users are about certain problems. So for different tasks, like for writing and math, you can have like different boundary levels, and then like try to learn a Kaufman reward function that works for all different different boundary levels and different non-decision time. So this certainly fits into that like idea, but I'm not exactly sure if the extension is trivial.
I see. Okay, thanks for that. Great talk.
Yeah, thank you. Huh? Yeah. Uh, that things would change. Things would change. Yeah. That's again studied, and we do not assume that here. but that's also well studied. Like in fact, like in diffusion models, people study various kind of evolving boundaries, all that. But the reason we consider E as a diffusion model is because this is a model people use if you actually want to recover parameters of the model. And like you can play with the boundaries as well, but then like you do not really get this Bradley-Terry expression that we had. Not it's not clear. The decision estimation coefficient. Yeah.
Double every time, say your time horizon, and every time at the end of the horizon, you estimate your parameters. Play the next like phase sort of.
Yeah, that's what we were discussing, right? Like you do this batch setting. In batch setting, you have this IID data conditioned on previous batches. And then you just do whatever you're doing here. What is not clear is that in each batch, how are you estimating nuisances? So like if you say that, yeah, for linear models, I use kernel ridge regression, then you need to show that, okay, this kernel regression has exactly this rate. And these are the samples that I use for estimating that.
It's a bootstrapping method that requires some like a initial guarantee on kernel.
Yeah. But it is certainly doable. Like, that's what we do. We assume that if you had an oracle that gave you some kind of rates on nuisance, then you get good guarantees. Yeah, yeah, yeah. Like this non-parametric regression is well studied. So, here's what you'll have to do. So let's say for linear classes, you figure out what is the property of this tan h by tan of Rx by Rx. Let's say R is linear, so tan of theta x by theta x. What properties this function satisfies? And then you figure out, okay, what should I do? Like if you want guarantees, then kernel regression would be a good option. Then you figure out, okay, I use these kind of this yeah, this RKHS space, and then this is the decay. So I mean, you just need to work out for linear what will you get, like what exact rates will you get. But huh? But tan h, the function is not tan h, right? It's tan of x by x. Non-convex.
Simpler problem which you mentioned a couple of times, which is that you also have scores for which there's like via which you construct your like in the experiments you can. So even there's some sort of possibility of traction. Right? Like I just even improve I mean the range improvement, for example, might even be applicable. There's no capital T, it's a much simpler setting. I give you you have to learn the reward function and I give you this, not even just the decision Y, but also instead of capital T, like these auxiliary scores.
Okay.
A much simpler setting, which, but the point is that now I again want to sort of bootstrap it with and not just use the standard log loss, but then again use this bootstrapping idea to get a, say, maybe convergence has like some is near best optimal, but they're dependent on range parameters or like these sorts of non like A and minus B. So I go back to a simpler setting,
Yeah.
but I still improve the results on other aspects.
Yeah, yeah, that's so you're saying like this T naught is this thing is known to you somehow.
Yeah,
Yeah.
tell you T naught,
Yeah, yeah.
but
What is this code now significant? How is it that it's
so it's giving you like like the other setups that I was mentioning earlier, right? I mean, you use it, so you get like reward values as well, and not just one.
In fact, like you could also think of, you don't exactly know T naught X, but you have some proxy for it, that how indecisive people are about these two options. That's all. You don't know the preference, but
There are data sets now like people give preference as well as confidence.
yeah.
Confidence would give how confident that they are. Those kind of data sets.
But then, like, I don't know how that would, if there exists a model to translate that to expected time directly.
Yeah, I'm saying forget time. Like your distance parameter is just R itself.
Okay.
And you also have auxiliary
Okay.
some, like instead of capital T, you have some
Other random variables.
other information, like the score
Mhm.
that I'm like, I like this more than this by 2 thumbs or 3 thumbs. And then
Basically, you're asking like if there's a framework where we can, if given any auxiliary observations, we can have a.
yeah. I mean, in effect, like the part is that if you give me this sort of nuisance or auxiliary, which is good enough, I can really bootstrap it. So I'm saying, fine, believe that it's good enough.
One thing is, one simple thing is let's weight it. When you compute this log loss,
Yeah.
take the weightage according to the confidence.
Yeah.
There is a very first sequence.
But like, I think the question would be that what is the underlying model in that case? Yeah. Because like in this case, you don't really need to justify why I do this. It's like, yeah, people have done it. Yeah. Thank you.
Like the size matters, I guess.
Oh yeah.
In case
Trying to get my hands on these when I was here.